Now we're going to talk about nested functions and the derivative of those nested functions. So before we're going to go into details and I explain you what I mean by nested functions, let's look at one example. So we all know how to take derivative of square root of t. Okay? That's not a difficult problem to do for us, now at least. We also know how to take derivative of 2t plus 1. Okay, that's even easier. But what if we kind of combine those two things together in some way and get a square root of 2t plus 1? And what we find now that is pretty difficult problem for us to do. Pretty much the only way we can do it is through the definition of the derivative through the limit, which is not a very easy thing to do. But it turned out there's an easy way to go around and finding the derivative by using kind of these two derivatives in some way, okay? And today we're going to talk about it, all right? So, but before we talk about this, let's talk about functions in general and what I kind of mentioned, nested functions. So, consider the function f of z, where z is an argument of this function, like this, z squared minus 2z plus square root of z, okay? And let's say we have this function and somebody comes to us and asks us, well, could you calculate f of 4? Normally that's not a problem. Normally the way we understand this is, well, let's assume that z equals to 4. Or let's substitute 4 in this formula instead of z. Okay, we can do that. And this is what we're going to get. And we'll be right for doing this. All right. Now, next somebody comes to us and says, well, I have the same f, but I would like to find f of t. That's probably also is not a very difficult thing to understand what it is. It's simply saying, well, I probably need to replace z with t. Or just simply say, well, z equals to t. So essentially, we do this, right? That's easy. But the next thing, when somebody comes to us and says, well, I would like to know what f of t squared is. That may be more problematic to understand what it means, but really we should follow the same kind of rule as before. We should say, well, our z is t squared now. And what we need to do, we need to replace z with t squared in a formal way. And this is what we're going to get. And if you do this, you'll be right. That's the right thing to do. Now let's say, well, I want to find f of g. Okay, well, it's the same way as f of t. We just change the, how the variable look like. Essentially, substitute g for z, and you get this. But what if I tell you that g is actually a function of another variable t? Well, in this case, what do I do? Well, nothing new. Same thing. We just simply replace g with g of t. So essentially when we're saying, well, I want to take a function f over an argument, which itself is a function, okay? So what it really means, just replace z in this formula, f of z, with this function g of t. And we're done with this, all right? So the functions that look like this, essentially there's a function g nested inside of the function f. This kind of things have different names. Some people call it superposition of functions, composition of functions, composite function. Okay? But it's a very interesting thing to know, and they're actually important in algebra to know. There's a different notation for this, so I'm going to show it to you. That sometimes people write it like this, sometimes people write it like this. But essentially, it's the same thing. Okay, it's a function of a function. It's a function where argument is another function. Okay. So, and let's just look at the function we have at hand. So we have a function of z, where z is an argument. And we also consider f of g of t, where g of t is an argument of our function, where we're just formally replacing z with g of t. Right? That's how we do it. But now let's be more specific. Let's say I have a function, g of t, as t to the fourth minus 1 over square root of t plus 7. I could have anything I want. What do I do in this case? Well, just follow the rule we described. Simply replace z with this value for g of t. And if we do, we get this big expression, which technically could be simplified. We can open this parenthesis because they're a square, and maybe we can kind of make it easy a little bit, but probably not too much. But that's not the point. Now let's make life a little bit more difficult. What if I don't want to have g of t, but I want a g of some other function? What do I do in this case? So let's say I have g of t squared minus 1. How do I deal with that? Well, same, we deal with g in the same way as we deal with t. So what we're going to do, we're just formally going to replace t with t squared minus 1. And you see, wherever we have t here, we have t squared minus 1 here. And that's what it means, g of t squared minus 1. But now let's assume we want to have my function f of an argument of g of t squared minus 1. How is that going to work? In the same way as before. Like we showed here. We formally, here we just, when we said f of g of t, we just replaced z with g of t. Well, now it's going to replace z with g of t squared minus 1. Or this formula. Okay? And in this case, we're going to have this kind of monster. Okay? But again, I hope you've understood the idea. Okay? And in fact, we can do this nesting many, many times. We can have f of the function of g, which is function of h, which is some function of, say, w of t, or something like that. Okay? So it's going to be superposition of many, many functions. All right. And the next question is, how do we calculate derivative of this superposition with respect to t, with respect to this argument t, which is not the argument of the function f, but the argument of a function g, actually. Okay? And to figure out how it should work, we need to go back to our definition of the limit, of the derivative as a limit of the value of a function point t plus delta t minus the value of the function at time t, okay, divided by delta t. Now, to make our life a little bit more simple, let's introduce notations. Let's call g of t here as z, and let's call delta z as the difference between g at point t plus delta t and point t. Right? In this case, our derivative is going to be f of z plus delta z minus f of z divided by delta t. Okay? The next thing, I'm going to do a trick. I'm going to divide this function by delta z. The next thing I'm going to do, I'm going to just rearrange terms. I'm going to, change the order of delta z and delta t, and replace delta z here with the difference in g. Okay? In this case, I'm going to get something like this, right? So what I did in the denominator, I simply switched t and z, and in numerator, I replaced delta z here with this definition, g of t plus delta t minus g of t. And now I would like to find this limit. Well, let's look at the last term. Okay, where this term gonna go when delta t is gonna go to 0? We say g. This is a derivative of g with respect to t. Okay? That's simple. Now, but what about this term? What about this f of z plus delta z minus f of z divided by delta z? Well, it all depends where delta z gonna go when delta t goes to 0. But let's look at the definition of delta z. It's g of t plus delta t minus g of t. So what's gonna happen to this guy when delta t goes to 0? Well, we're gonna have g of t minus g of t, which is 0. Which means that when delta t goes to 0, delta z goes to 0. And now the question, what's going to happen with this thing when delta z goes to 0? And I say, well, this is simple. That's simply a derivative of this function f over its argument, which we call z. Okay? And now we got our formula for the derivative of a superposition of two functions. And that's going to be derivative of f with respect to its argument, which we call z, times derivative of g with respect to its argument t. Alright? What I wrote here has a name. It's called chain rule. Okay? A chain rule is used very, very often in calculus when we need to calculate derivatives of rather complicated functions. So let's move on. So again, this is how we're going to calculate derivative of superposition of the function. It's df dz, its argument, times dg dt. The only thing we need to know here is that z is actually g of t. Okay, it's not just some kind of random argument. So let's go back to our original problem. How would we do this? If I want to calculate d dt of square root of 2t plus 1. Well, one thing is, you could see that this is square root of something on the square root. You can say, aha. In this case, I can say I have my function f of z as a square root of z. And now my z is going to be this function. Okay? I'm going to introduce the function g of t as whatever sitting on the square root. Alright? And now we can see that f of g of t is exactly our function. Right? And now how do we calculate derivative of this? Well, it's derivative of this with respect to its argument. It's 1 over 2 square root of z times the derivative of this guy, which is 2. Again, the first function f is with respect to its argument z, the second function with respect to its argument t. Okay? And now what we need to do, we need to multiply both of them together. This is what we're going to get. The next, well, one thing is we notice there's two in denominator, 2 in numerator. We can cancel them out. The second thing we need to note is that we're not interested in derivative with respect to z, but with respect to t, so we really need to convert that z back to t. And remember, z is g of t, which means that z is this guy to t plus 1. And if we do this, this is our final answer. Okay? Again, this is much, much easier than if you tried to go through the limit. Try to obtain this formula through the limit. Okay? So let's look at another example. I want to get derivative of sine of t squared plus 1 over t. How do we do that? Well, I can immediately see this thing is a superposition of two functions. One is sine, another whatever's inside of it. Again, we take f of z as sine of z. And my z will be like g of t, which is t squared plus 1 over t. Right? And, well, what is the derivative? Well, it's derivative of f times derivative of g with respect to their respective arguments. Derivative of sine is cosine. Derivative of g of t is 2t minus 1 over t squared. And all we need to do is now just put those terms here, okay? The last thing we need to do, we need to basically get rid of z. We need to remember z is g of t, is this thing. So, and if we put it inside of cosine, this is what we're going to see. It's cosine of this argument times this parenthesis. All right? It's easy, okay? Easy. As long as you know how to calculate derivatives of these functions. Now, let's look at a little bit more complicated example. In this example, we will have to use our formula for superposition of functions, or derivative superposition of functions, not just once, actually twice. Okay. So let's look at this as derivative of this argument put in the power 8. So immediately, well, f of z is z to the 8, and z is going to be whatever's sitting here, right? This is my g of t. Okay. So to calculate derivatives, I need to calculate derivatives. So this, guys, this is what I'm going to get. Next thing I want to do, I want to multiply them together, and this is what I'm going to see. All right. Now I want to, again, what we'll do, we'll replace z as g of t, but there's one complication. When we take derivative of g, we saw that derivative of g is derivative of t cubed, which is 3t squared, plus derivative of the second term, which now I just wrote as a derivative of that term. I didn't really open it up, because to open it up, we really need to use our procedure one more time, okay? So, and let's look and find what this term is actually is, okay? Again, it's 1 over square root of 7t plus 8. So, we can look at it as a superposition of two functions. One function is 1 over square root of some argument. So we don't get confused, I'm not going to call this function as f, I'm going to call it as h, and I'm not going to use z because I used z before. Here, I'm going to use u instead. Okay. In this case, my function h of u is 1 over square root of u. Just to remind you, we needed to calculate derivative. That 1 over square root of u is u to the power of minus 1/2. And u in this case is going to be whatever inside of the square root is 7t plus 8. Okay. And in this case, I'm going to call it p of t. Okay. Now again, we take derivatives of both of those functions, h and p, with respect to their own arguments. And now we know that derivative of superposition of the function is the product of these two guys. So I really just, for brevity, I just already substituted 7t plus 8 instead of u in this formula, and I got this result. Okay. And now, well, what do we need to do? We need to substitute this value right here, and also we need to replace z with g of t. Okay. And if you do that, this is what you're going to have. And that's our final answer. Well, obviously, we could say, well, we can maybe simplify this formula, maybe, maybe not. But really, that's not really calculus anymore. It's some algebra. And I'm going to leave it for you. All right?